Hello, student. Welcome back to this phenomenon of scattering and the method of partial wave analysis of this scattering phenomenon. So, in the last session, I discussed about the partial waves and how that concept is introduced here. So, in this session, I will going to study the scattering by a central potential case with the help of this partial wave analysis. And here, actually, we are trying for the asymptotic solution of this present case. And the scattering equation that describes the scattering phenomenon is given by this equation. So this scattering phenomena is a phenomenon where where the two particles are interacting with each other. So this is a two particle system. Because of this reason, we can call this as a two particle system. So for a two particle system, the Schrodinger equation is given by this equation, which is minus x cross square divided by 2 mu into del square psi plus V of r psi is equal to E psi, where this mu here is equal to m into small m into capital M divided by small m plus capital M. And this mu actually is the reduced mass or the center of mass of the two particle system. Because whenever we are considering a system of two particles, we have to always look for the reduced mass or the center of mass of the system. So here this mu represents the center of mass of the two particle system. And this small m is the mass of the incident particle, and this capital M is the mass of the target. So in the present case, we assume that this target is stationary and which is kept at the origin or one place or one point. That point we have taken here as the origin. And another particle is coming towards this target particle. And as I explained in my earlier sessions, we can consider a sphere of potential around the target material or the target particle. And if the incoming particle is inside that sphere of potential, then only it interacts with the target atom or target particle. Otherwise, it doesn't interact with the target particle. That means if the incoming particle is out of this sphere of potential, then there will be no interaction between the incoming particle and the target particle. So the wave function psi has to be independent of phi, as the incident particles are along the z-axis. So actually this phi represents the angle between the plane containing the incoming particle and the containing the scattered particle. So this is not important here because we have considered one particle, and that particle is moving along the z-axis. The solution of this equation 1 in spherical polar coordinates is given by this equation 2, and it's psi of r comma theta is equal to RL of r into PL of cos theta, where this L, which is the order parameter of the legendary polynomials, L is equal to 0, 1, 0, comma 1, comma 2, dash, dash, dash. This PL of cos theta is actually the term coming from the legendary polynomials. And this RL of R satisfies the radial equation of the two-particle system given by this equation. So this is 1 by R square into d by dr of R square into drl by dr plus the terms in this bracket into RL is equal to 0. So this is equation 3 is nothing but the radial equation of the scattering phenomena. So outside the range of the potential, R is greater. That means when the radius of the sphere, the R is greater than R naught. So R naught is the radius of the sphere of potential. That means a sphere is assumed to be present over the around the particle which is kept at the origin, whose radius is R naught. That means when the incoming particle is outside the sphere, then the radius will be definitely more than this R naught. So therefore, this condition R greater than R naught means the particle is outside the range of the potential. So this equation reduces to the free particle equation as like this. So actually what we have done here is that this term is differentiated with respect to R using the product rule, and it is written here. And as I told, outside the range of this potential, the potential means that particle is not interacting with the target particle. So because of that reason, that particle, incoming particle, passes the target particle without scattering or without interacting with each other. So for that reason, we can consider this incoming particle as a free particle because there is no interaction. And that is why we have kept this V is equal to 0 in equation 3, where this V is the potential. So since the particle is outside the range of this potential or outside the that potential of sphere, so there is no interaction, and hence this particle can be considered or treated as a free particle. And for a free particle, this potential is 0. So that is why this term goes 0, and this term we have written as k square. K square is equal to 2 mu E upon h cross square, and we have set V is equal to 0 for the free particle case. And the first term is differentiated and is written here. So we got the equation 4. So this differential equation 4 has two independent solutions, which are JL of KR and NL of KR, where JL of KR is the spherical Bessel function and NL of KR is the spherical Newman function. So as I stated earlier, the knowledge of spatial functions is needed here. And so this equation 4 is having two independent solutions, one in the form of spherical Bessel functions and another one in the form of this spherical Newman function. The general solution of this equation 4 is then written as RL of kr is equal to A dash JL of kr minus B dash NL of kr. And where this A dash and B dash are constants. Though the function NL of kr is not finite at r is equal to 0, it is retained as we are interested only in the asymptotic solution. That means actually, so this function NL of kr is not finite at r is equal to 0. That means r is equal to 0 means at the center or the origin. So that is why still it is retained because we are interested only in the asymptotic solution. And for small and large values of kr, we have this Bessel function can be written in this way, that is 1 by kr into sine of kr minus L5 by 2. And this Newman function is written as minus 1 by kr cos of kr minus L5 by 2. So these two functions we are writing in this way when for small and large values of kr. So now we have to substitute this equation 6 into 5. This is the equation 6. So equation 5 is here. So you substitute equation 6 into 5. Means we have to substitute the values of this JL of kr and NL of kr. So what you are getting is that equation 6 is coming in this way. So it is A dash by kr, and in the place of JL of kr, I have substituted the value of JL of kr. It is 1 by kr into sine of kr minus L5 by 2 plus B dash of B dash into NL of kr. The value of NL of kr is here, and this minus sign becomes a plus here. And so it is B dash of kr into cos of kr minus L5 by 2. So in this way, I got equation 7. When the potential VR is not equal to 0, that means when we set this condition, the incoming particle is within the sphere of potential. The incoming particle is within the sphere of potential. And that means the particle will be definitely going to interact with the target particle. So that is the point. So when the potential VR is not equal to 0, this is for the incoming particle, the value of the constants B dash of L divided by A dash of L has to be determined by solving the equation 3 inside the scattering region. So inside the scattering region means inside the sphere of that potential, and then matching it with the asymptotic solution of equation 7. So for that, so writing the new constants AL and delta, constants AL and delta L in terms of A dash and B dash by the relation, because for the incoming particle, VR is not equal to 0 means that is inside the sphere of potential, and therefore the constant are also changing here. So this A dash, the constant A dash becomes AL cos delta L, and the other constant B dash becomes equal to AL sin delta L. So we have to substitute these constants A dash and B dash into the asymptotic solution of equation 3, which is nothing but the equation 7. So here equation 7 is there. You have to substitute these two new constants into the equation 7, and therefore the equation 7 becomes like this. So this is the equation 7, and this becomes RL of KR is equal to A dash was here. So in the place of A dash, now I am writing this thing AL cos delta L. So this is the AL cos delta L is there, and this is written as it is. And in place of B dash, we have to write AL sin delta L. So that is written here, and remaining is as it is. So when we substitute these A dash and B dash into the equation 7, we are getting a standard form of a trigonometric function here. So this is sin A cos B, sin A into cos B plus cos A into sin B is equal to sin of A plus B. So that form we obtained here, and therefore this equation reduces to the form AL by KR is AL by KR into sin of KR minus L5 by 2 plus delta L. Treating this KR of L minus L KR minus L5 by 2 as a and delta L as a B. So I took the form of sin of A plus B, and as usual, this L takes the values 0, 1, 2, dash dash dash. So these are delta L's. What are these delta L's? These delta L's are called the phase shifts. So they represent what is the phase shift between the two waves which are generated by the two particles because of their interaction. So one wave is generated because of the incoming particle, and another wave is generated because of the interaction of that incoming particle with the scattering particle. So what is the phase difference between these two waves is measured by this quantity that is delta dash L. So these are the and the phase shift delta L measures the amount by which the phase of the radial function for angular momentum quantum number L differs from the corresponding one for the V is equal to 0 case. That means actually we are looking at the change in the angular momentum of the incoming particle before scattering, and the change in the angular momentum that the same particle after scattering. So V is equal to 0 means that is the case of before scattering, and V is not equal to 0 means that is the case after scattering. So what amount of momentum is going to change, that also decides the change in the phase of the two waves. So that change in the phase of the two waves is given by this delta L parameters. So the most general asymptotic solution is then given by this equation. This equation, that means we have to substitute that equation 8 into equation 2. So this is the equation 2, equation 8 is there. And here we have the equation 2. And here, because we have initially assumed that the solution is of this form, and we are substituting this value of this RL in this equation 2. from the equation 8. So this is the equation 8. RL is equal to RL of KR is equal to AL divided by KR into sine of this thing. So substitute this 8, equation 8 into equation 2. You are getting the most general asymptotic solution as the psi of r comma theta is equal to summation of L is equal to 0 to infinity and AL upon KR and sine of KR minus L5/2 plus delta into PL of cos theta. And where this AL is referred as the asymptotic amplitude. So now in this session, I got an expression for the most general asymptotic solution of this scattering case. And in the next session, I am going to discuss this phenomenon, that is the scattering amplitude. Thank you for watching.